How you doing? I'm Mr. Rose, and we're going to continue to talk about our electric field, and we're going to continue to use things from Newtonian mechanics, specifically free body diagrams, Newton's laws, to understand how we can keep applying and moving forward with physics. It's actually pretty simple, pretty straightforward, pretty powerful stuff. Also, I have a little bit different setup, so if it looks like I'm looking at nothing, I got this question way up here, and it's easier to read it there than it is to read it there. So sit back, enjoy, and let's do some physics. I'll give you a second to read the question. Now that you've read the question, some highlights. We know that the two masses are the same, and I know that they have a value of 2m. I'm going to start by listing my variables. m1, which is equal to m2, is equal to 2m. What else do I have? I know that I have two charges. I asked you to make a drawing, and I asked you to see my drawing. It says IE. They're in the same plane. See the figure I drew. I didn't draw that figure because I'm hoping that you're going to attempt to do that yourself. But now that you've done that, hit the pause button, you've done that figure. There's the ceiling. I'm going to show you just a kind of little cheat. It says they're on the same plane. That's actually going to become important. But it says that the masses are the same size and the string length is different. So instead of starting with the string length, start with the same plane. Here's M1, theta 1, which we know from the problem. Theta 1 is equal to 35 degrees. Perfect. And now a different string length way over here. That looks very close to the same, so let's do that differently. Way over there, beautiful. There's my mass 2. At some undisclosed theta 2. So, yeah, that actually pretty much seems like that's all we know. We're looking for, I think I know the charge, if I remember. I know the charge later on. That's all that's given to us in the problem. So, we are looking for the size, move my calculator around, we're looking for the size of theta 2. Angle of deflection. So the way that I'm going to start this is, yeah, you guessed it, I'm going to draw myself a free body diagram. So that free body diagram, well, I'm going to start with mass 1 because I know the most amount of stuff in mass 1. So free body diagram for mass 1. I know I've got that tension force there. I know I've got an mg that's going in that direction, and I know there's an electric force. Oh, that is something they told me in the problem. I know these two have the same charge, and they are separating, so I definitely know they're the same charge because like charges repel. So I could have assumed that from, well, I knew this. I could not assume the same size charge, but I could assume the same, either positive or negative. They told me in the problem it was the same size. So here's my free body diagram, and we should know, if we remember from Newton's laws, obviously, this tension is not in the x or the y plane. So we're going to break that down into a tx and a ty. And I know theta 1 is up there. So I'm going to now solve. Now I know we can do, if I know this angle, obviously I know this angle, but I'm going to work with only the given information. They gave me that 35 degrees, and spoiler alert, I kind of know where this is going, so it's going to be easier to use that as well. If you decided to try it with this angle down here, not a big deal. We should end up with the same answer. It's just mine's going to be a little bit simpler and a little bit cleaner. So I know I need to break things down. I know that my electric force is equal and opposite to my Tx. I know my Ty is equal and opposite to mg. So I know I'm going to start in the y direction just because I want to. I know that equals ma. I know that equals 0, obviously. So in my y direction, I'm going to say I have t. So, I'm going to do the y direction. So I'm going to bring that over there. Bring that over there. I know this ty and that ty are the same. This theta 1 and that theta 1 is the same. So I'm going to say T1 or T cosine theta 1 minus Fe equals 0. T is equal to Fe divided by cosine theta 1. Hope I did that correctly on the fly. But yeah, it looks right. Those are alternate angles, so that should be right. Now I'm going to work in the x direction. I'm going to say, put it over here, fx equals ma. And fx is going to be, I'm going to use this top angle here. So I'm going to say t sine theta 1. T sine theta 1. That and that are the same. Minus, that's not an Fe. Hoping you were like, Mr. Rose, what are you doing? This is equal to mg, so minus mg. Mg over, that's way better, mg over cosine theta 1 minus Fe equals 0. Move that up a little bit so we can get more on the paper. So this is going to be T sine theta 1 is equal to Fe. Well, what is Fe? Fe is kqq over r squared, or 1 over 4 pi epsilon naught qq over r squared. Since the charges are the same, I'm going to say this is 1 over 4 pi epsilon 0 times q squared over r squared. So there are my components. Remember, I'm trying to solve theta 2, and I haven't actually even done anything like that. But, and actually right now it looks like I can solve part B. Almost solve part B. Let's see. I've got two equations. I've got one unknown, but I know t and t are the same. So I'm going to say mg over cosine theta 1. Now you probably see why I chose that angle. But if not, you're not going to have you're not going to have sine over cosine. You're going to have a cosine over a sine. Really not a big deal. Times sine theta 1 equals 1 over 4 pi epsilon 0 q squared over r squared. Yeah, I could definitely solve, assuming the mass and the charge, the distance. I could definitely solve that distance at this moment in time. Sine over cosine is tan, so I've got mg tan theta 1 equals 1 over 4 pi epsilon 0 q squared over r squared. And I know the value of theta 1 was given as 35 degrees. So we could plug some stuff right there and solve out. But that wasn't what I want to do for part A. So we can have the same exact setup for theta 2. It'll be the exact same same setup. And I actually did just realize, that was my pause there, this m1 equals m2, that was my mistake. m1 is equal to 2m, m2 is equal to m. So I'm going to go back up here, and I know these were all m1, so that's not a big deal. That's an m1. And I'm going to say m1 was equal to 2m, m2 is equal to m. This is good when I come up with problems that I mess up myself. So now that I've corrected that, we solved this whole thing in terms of m1, theta 1. It would be the exact same setup like I said, and I challenge you to do it. Draw yourself a free body diagram, break things into components. You should be able to come up with, on the other side, for m2, you should be able to come up with, I'll put it way up here, m2g tan theta 2 equals 1 over 4 pi epsilon 0 q squared over r squared. So this is nothing new. It's symmetrical. You should know 100% this is M1. I'm sorry, this is solving for theta 1. This is solving for theta 2. And now 1 over 4 pi epsilon 0 q squared over r squared. 1 over 4 pi epsilon 0 q squared over r squared means I can set that equal to that. So I would have M1 G tan theta 1. I know everything on that side is equal to M2G tan theta 2. Sub in my values for M1 and M2. As I said, M1 is really 2mg tan, I guess I can put in my 35 degrees here because we're just about solved, is equal to mg tan theta 2. And I get rid of my m, get rid of my g, get rid of my m, get rid of my g, and I am left with 2 tan times 35 is equal to tan theta 2. I just dropped my colors, but such is life. So now I have the inverse tan of, that's weird to write, inverse tan of 2 tan 35. Make sure we're in degrees, equals theta 2. Some calculator magic. The inverse tan, there we go, of 2 times the tan 35. I'm in radians. Nice job, Mr. Rose. And you get theta 2 to be 54.47 degrees. So like I said, if you chose what you may have done in the beginning, if you chose to use this angle instead, that'd be fine. Instead of sine over cosine, you're going to end up with a cotangent or 1 over tan. Doesn't matter. You'll come out with the same thing. You should get theta 2 equal to 54.47 degrees. And now part B is find the radius. So part B should be pretty trivial. We know given M1 is 0.03 and Q is 5.5 times 10 to the 55. So I can just pick this guy right there. So I can say 0.03 times 9.8, drop my units because I'm a bad person, but I'm pushing a time limit here, times the tan of 35 degrees should be equal to 1 over 4 pi epsilon 0 q squared. What Q it gave me was 5.5. 5.5 e negative 10 divided by r. I should be able to solve for r. Some calculator work. And you should get an r equal to 8.1 times 10 to the negative 5 meters. That is all I have for you today. I hope you started to see, you're starting to see how we can use mechanics, all this knowledge we already have, to solve for somewhat of a complex electric field and electric force problem. Please feel free to like, comment, or subscribe. And yes, you will see me next time.